The trigonometric functions are referred to as circular functions when the domain is measured in radians. We can see how the sine function is related to a circle by considering ordered pairs on the unit circle. The unit circle has equation x squared plus y squared equal 1, and the coordinates of points on the unit circle are xy, where x equal cosine s, y equals sine s, and s is an arc on the circle with initial point 1, 0. As we rotate around the unit circle counterclockwise, the points on the unit circle repeat after each full revolution, which is equal to 360 degrees or 2 pi radians. This is why the period length of cosine s and sine s is 2 pi radians. Furthermore, we can use the points on the unit circle to help draw a sketch of the sine and cosine function. In this animation, you can see the rotating point on the unit circle and how this relates to tracing the graph for the related sine function. Each time the point goes around the circle again, the sine graph is retraced. Note, in reality, the sine graph continues infinitely to the right, but I am using this visualization for simplicity. Along with saying that the circle is retraced every 2 pi radians, if we rewrite our coordinates by letting s equal 2 pi t, where t stands for time in seconds, we can say the circle is retraced once every second. The coordinates would then be written xy, with x equal cosine 2 pi t and y equals sine 2 pi t. In the next animation, the point is going around the circle 5 times as fast. In this case, the coordinates are xy, where x equal cosine of 2 pi times 5t and y equals sine of 2 pi times 5t. The period for these functions is 2 pi divided by 2 pi times 5, which is 1/5, which means one cycle of the sine graph would be drawn every 1/5 of a second. This also means that the frequency is 5, which can be interpreted as 5 cycles every second. We use the word frequency because it describes how frequent the graph of sine appears in the time period of 1 second. Comparing these two animations, the first sine graph has a frequency of 1 cycle per second, and the second sine graph has a frequency of 5 cycles per second. The connection we can take from this is, the faster the rotation around the circle, the higher the frequency. Furthermore, since frequency is related to pitch, the higher the frequency, the higher the pitch. There are few ways to create sound from circular motion. Maybe you or a meddling relative have been bored at a family dinner and started using glasses to make a sound. If your finger has just the right friction with the rim of the glass, rotating your finger around the glass can create a sound. In fact, this sound has a pitch or frequency. But this frequency is not dependent on how fast your rotation is. It depends on how much liquid is in the glass and the resonant frequency of the glass, which is the same frequency if you were to tap on the glass with a spoon. This method of making a pitch was made into an instrument by Benjamin Franklin called the glass harmonica, where up to 10 glasses could be played at once, one for each finger. Another instrument that uses circular motion is the Hurdy Gertie. This takes the mechanics of a violin, bow against strings, and puts the bow onto a circle that is turned with a crank. The circle touches the string and causes it to vibrate, and the change in frequency is dependent on where the finger presses on the string, similar to a violin or a guitar. However, again in this case, if the crank is turned faster, the pitch does not change. But there is a great example related to our discussion of rotational speed and pitch, and that is the tone wheel organ. This is one instrument where frequency does depend on the speed of rotation of a circle, and the most famous example is the Hammond organ. At its heart is a motor driving a gearbox of rotating discs. These discs are like the disc on a bicycle that drives the chain. They have raised bumps on the edge of the disc. The frequency depends on the number of bumps and also on the speed of the rotation. The sounds are picked up via electricity and then amplified. When sounds from many spinning discs are combined, we get a sound heard in many churches and theaters since the early 20th century.